Hey lovelies, welcome back. Okay, so today's topic is CX bond, that is between C and X, the bond which is present. What is the nature of it? That is what we are going to learn today. Okay, so here C refers to carbon, and X refers to halogen. Okay, so what is the bond which is present between carbon and halogen? That is what we'll be dealing today, the nature of that. Okay, so here you should know one thing, students. Electronegativity of halogen is very much higher when compared to carbon's electronegativity. I hope you remember this. We have learned in 11th standard. That is, electronegativity of halogen is very much high when compared to carbon's electronegativity. Here, electronegativity, what does it mean is, it refers to the ability of the atom to attract bond pair of electrons towards itself. Okay, that is ability of atom to attract bonded pair of electron towards itself. That refers to electronegativity, and that is very much higher in group number 17. This electronegativity is very much higher in the group number 17, that is the elements fluorine, chlorine, bromine, iodine. These elements have very much high electronegativity because by taking one electron they get octet structure, stability increases. So these elements are very powerful electron withdrawing groups. Okay, so you should know one thing, in the whole periodic table fluorine is considered to have highest electronegativity. Okay, and the value is 4. So what is it? In the periodic table, element fluorine is considered to have highest electronegativity. Since halogen is very much electronegative, what it does is, it will attract the bond pair of electrons towards itself. Okay, halogen, what it does, it will attract the bond pair of electrons towards itself, due to which a bond will be slightly shifted towards halogen atom due to its electronegativity. Because of which our halogen atom will get partial negative charge and our carbon atom will get what? Partial positive charge. Okay, since now you can see that there is a polarity between these two bonds. Okay, there is some polarity which is created between these two bonds due to partial negative and positive charge. You should know one thing here, students. Here the amount of charge, okay, with the increase in electronegativity, our charge value also increases. Here the charge value of us will be directly dependent on what? Electronegativity. As the electronegativity increases, the charge value will also go on increasing. Okay. Now, due to this polarity, whatever is created in this halogen and carbon bond, what happens is a dipole is created. Okay, what is that? A dipole is created, that is nothing but two poles, that is positive and negative pole. Now why is this dipole created? That is because of the polarity which is developed in this bond. Now why is this bond polar? The bond is polar because of the electronegativity of halogen atom. Okay, now here we have halogen atom. It can be anyone. Okay, it can be fluorine, chlorine, bromine or iodine. It can be any of these things. And you know one thing, here our size of the atom goes on increasing as we move down the group. Here fluorine will be the smallest one in size, whereas these things will be going on increasing as we go down the group. Let's talk about the kind of bond which is present between carbon and halogen atoms pictorially. Okay, suppose I take this as carbon atom. This is carbon atom and I'll consider fluorine. You know one thing, students, as in the periodic table, as we go along the period, what happens to the atomic size? It goes on decreasing. So if I consider this as carbon, I'll be considering this as fluorine. Why I have overlapped is, you know, when we form a bond, there will be overlapping of atomic orbitals. So this is the kind of bond which is formed between carbon and fluorine. And if I have to talk about the bond length, you know, bond length is nothing but internuclear distance, right, between two atoms. So here, if I take this as fluorine and this as carbon, so this is the kind of bond length which we can see in carbon and fluorine atom. Moving on, suppose again I will do carbon atom. This is carbon atom and I will take this as chlorine. Okay, I will take this as chlorine. Now we will see here again, if we check, when compared to this, this bond, whatever the bond length is there, when compared to fluorine atom, it has increased a little bit. Now moving on, suppose I take again this as carbon atom. I'm going to take little big one, carbon, and here again this will be bromine. So you will see that the bond length again increases when I see along this, okay, carbon chlorine and carbon bromine. You see this will be having much higher bond length. Now moving on to the final one. This is carbon and I'll take this as iodine, okay. So if you see here the bond length of carbon and iodine, if you see this will be the highest one. If we see all the 4 diagrams, which is having the highest bond length, that is carbon and iodine. So you should know one thing, students, if they ask you the order of bond length, how is the order of bond length, you have to always say that. I'll just write it here. Carbon and fluorine, the bond between carbon and fluorine, bond length will be very less when compared to carbon and chlorine. That is also lesser when compared to carbon and bromine, which is lesser to carbon and iodine. This is the bond length order which is shown here. Now we are going to learn about the order of bond dissociation enthalpy. First you have to understand the word, students. Here what is meant by bond dissociation enthalpies? Enthalpy is nothing but energy. That is the energy required to break a bond. That is known as bond dissociation enthalpy. You should know that smaller the bond, higher is the energy required to break that. Suppose I take example of chopstick, okay. You see that here the length is a little much high. So I can break it very easily. Suppose I take a smaller chopstick and try to break it. That is little difficult. That is, smaller the bond, higher is the energy required to break it. So you know that the order of bond dissociation enthalpy will be completely reversible of bond length. That is, it will be somewhat like this. There we wrote like this, isn't it? So this is the order of bond length. So how is the order of bond dissociation enthalpy? It will be reversible of that, because of the size, okay. Here carbon and iodine, between them the bond dissociation enthalpy will be very less. The energy will be very less required when compared to carbon and fluorine atom.